ועומר
do like dogs and cats.
So today we want to find the Margulis function. We show that last time we proved the following theorem. Last time is if you have a group G acting on a, say, locally compact space, locally compact space, and you have new probability measure of G, and we suppose that there was this star condition that there is no non-constant function in L2 of X with respect to a measure sigma invariant under all G in the support view. So that's the assumption. That's the algorithmic assumption. And then the main theorem is the main condition that there is a proper Margulis function f on X, then the measure of X is fine. And the Margulis function is with respect to the measure mu. Yeah. With respect to the measure mu, Margulis function f is, let's say, mu Margulis function if the convolution of f with respect to mu is smaller than c times f plus b at any point for some c which is less than 1 and b that. So that's what we are looking for. We want to find, in our case now, we will consider X to be G mod gamma, where G is a semi-simple group and gamma is an arithmetic group, and we want to find some Margulis function for that space with a Haar measure on G mod gamma. We will do it for G, which is SLN, and gamma is SLNZ, and later we'll deduce that the same function works for every rationally defined algebraic subgroup inside SLN. So and it will work for for all arithmetic groups in all semi-simple groups. I want to say something. So in my work with Margulis and Arya, we fixed G and we found a Margulis function which worked for all lattices inside G, not just arithmetic. In fact, for all discrete subgroup inside G. But for a group which is not this a lattice, it wasn't proper. So that's the only difference was between finite and infinite volume was the proper function. But the same function works for all satisfy this condition for all gamma in G. Now, and the function we construct was 1 over the injectivity radius to some power. Let me do something with it.
זה קרה כבר פעם, אתה זוכר?
כן,
גן או... אפשר לכבות את המסך בלי לכבות את הזה? אפשר לכבות רק את המסך, לא?
כן, לכבות את המסך. And what Margulis does is it's something else. So he finds a function, some Margulis function which works for only for arithmetic groups, but not just for G, but also not for just for SLS, but for every subgroup.
אין שם שאלה.
זה השאלה.
לא, זה שאלה.
So for every so for every algebraic subgroup. So it's a different approach. I think we had to work harder technically, and we had to rely on the idea from the work of Gelander and Margulis and other stuff. But what we do works also for non-arithmetic groups. While okay, well, I don't know what I'm trying to say. I'm just trying to say that maybe it worthwhile to try to combine both methods and find something that works for simultaneously for all lattices and for all subgroups inside G, and maybe deduce some variant, some strong finiteness theorem. I don't know, like Prasad, Borel. I don't know. I think maybe one can get a new result by trying to combine both the approach that I described today and the approach that I described in my paper with Margulis and Arya, which is a different approach to construct the Margulis function. So each had a different goal. And so, okay, so today will be a bit technical, at least the first 1 hour. And so the title I would like to for today's talk is construction a Margulis function. And okay, so we start with some general lemma, computational lemma. So let be a finite dimension vector space, and we denote by S plus V the set of positive definite self-adjoint positive definite self-adjoint matrices transformation. So in particular, V has some inner product. And this will be the first time. Lemma 1. Let G be a locally compact group. Rho representation. Continuous. U probability measure G. And suppose that the support of mu or the image of the support of mu is in the positive definite matrices, and that mu is symmetric. It is clear what I mean. not asked. And also that log function log for G is integrable. So here I take just the operator norm, transformation. Then for every V, we have the integral over G log of GP is U, at least log. Furthermore, place there is strict inequality unless V is an eigenvector for any G in the support. And equality all if and only if V is eigenvector for every G in the support. Eigenvector for this is basically
It's just wrong.
Option. Approaching you.
this follow from the fact that U is symmetric and Cauchy-Schwarz inequality.
What it was for how twice?
בטעות. טעות, זה ראש של ספורט, נראה לי.
Okay, so let's take back proof. So the integral G over G of log or G V mu equals okay. Half the integral of G log or GV plus log of G inverse. This is because mu is symmetric. Okay. Which is the same as half integral of G log OG V times OG inverse V, which by Cauchy-Schwarz. So this is because mu equals mu inverse. And now I use Cauchy-Schwarz to say that this is at least at most half of log the inner product for G V with the wrong G inverse V. No, bigger. Schwarz is the other direction. You see, there is equality, okay, I will give you the inequality in a moment. Okay, which is
Is it just Cauchy-Schwarz, or don't you need like a Janssen or something?
Yes.
With the integral inside the log or something?
So yeah, and now these matrices are self-adjoint. So just let me just write it. So this is half. Okay, the integral. Sure. Integral, and yes, so integral, and then half, and this is the same as half of log VV, which is okay. That's good. That's the proof. Now I should say something about equality. Okay, Sarah? What's the problem? That's good.
No, it's okay. Yes.
That's okay. That's Cauchy-Schwarz. Now, equality here holds in Cauchy-Schwarz only if these two vectors are proportional. Equality implies or equivalent to V being eigenvector of rho G square for every G. Now we assume that these matrices are positive definite and symmetric, and this is equivalent to being eigenvector of one. So for if you have positive definite matrix, you are eigenvector of the square if you are, or if and only if you are eigenvector of the original matrix. So that's about the equality. Okay, so that's yeah, I warned you today will be a bit computational, so maybe I'll keep that, or you remember this. Okay, the next level will be a consequence of this one, and together with some compactness argument. I want to say that if you have condition star, so you have here strict inequality, and then by some compactness of okay, let me just so I'll delete it, and you remember the question. Did some notation, so we denote by let's wedge I of Rn denote the I exterior power
Ça va même, c'est.
with inner product and norm induced from the standard one. Okay, it's here, right? If I take an orthonormal basis for Rn, you can produce from it orthonormal basis for the wedge power, and then determine the inner product and the norm. if you have a Borel representation of some group into GLNV, then you have rho I is a representation G to the exterior product GL which I and the induced representation. Actually, okay, sorry, there's no G. Just noting well, I it's the representation from G, L, and R to G, L, which I, N, canonical. And we denote by WI the set of all vectors of the form V1 wedge VI such that V1 and VI are independent. So we can observe that this is a transitive, it's invariant and transitive. WI is GLN invariant and transitive. And also it's compact, that what will allow us to reduce the next compact. Projectively compact. Okay. So, for those who arrived late, I am describing Margulis' approach to construct the Margulis function, and this will be a Margulis function on SLN on SLN R mod SLN Z actually on the, but it will induce Margulis function for every arithmetic group in every rationally defined subgroup of SLN.
Can you explain what is it compact?
What? The Glassman variety? What's the Glassman?
You said WI is compact.
WI is compact. Is there, I projectively compact. What? Projectively compact.
What do you mean?
It's not inside, it's image in the projective space. In the project, I mean, if you, active, like if you divide by scalar. If you want projective space is complex. If you want, it's closed. It's closed, and therefore, if you intersect it with the normal sphere, if you want to divide by
close to where in the projective space of lambda I.
Just ignore what this is. We will use it in the proof of the next lemma, and then you will see lemma 2. Suppose that mu is the probability measure on GLN are satisfying the following three conditions. One, mu is symmetric. And the following condition will be required also later, so I want to remember them. The support is compact. And contained in the set of positive definite symmetric matrices. And 3 is that the group generated by this support is irreducible. Then, and actually, okay, for every delta small enough, sufficiently small, there exists some constant depending on delta, which is smaller than 1, that's crucial here, such that for every I between 1 and n, and for every v in wi, this is we have that the integral of 1 over rho I g v to the power delta is bounded by this constant. Okay. So if you want, this is almost what is written. Like if instead of C, I would write here 1, then it will be like basically what was written before. And now, assuming that this condition will imply that there is no vector in any wedge representation, there is no vector which is invariant under the support, and therefore the equality from the previous lemma will not hold, and therefore it will be strictly smaller than 1, and by some compactness, there will be some C. So that's a brief explanation of the proof that I'm going to write now, but I will write the proof and then you will see, exactly.
Why do you like only delta which is smaller? It doesn't mean if you make delta bigger, you can just take the same with delta, right? Oh no, because you divide by v to the power.
Okay. And divide both sides. You will see in the proof. I mean, I'm going to like payload extension. So we need a small delta. So by the previous lemma, we have the previous lemma implied that the log of rho I g let's just write it as it was, yeah, log of rho I g b the mu minus log v equals to the integral of log of I g v divided by v, the mu, which was positive. That's the previous lemma and condition that the action is irreducible. Right? I don't want to write it, but is it clear? Tal, you would write. No. So this implies that there is no invariant vector. The action is irreducible, so there is no invariant vector in the ith exterior power. In particular, v is not invariant vector, and this, so for some, so this is always bigger than this, and for some it's strictly big. Let's some So this is always non-negative. This is at least one, this is non-negative, and for some G in the support it's tricky, but that's from the previous lemma and condition 3. Now, using the fact that Wi is projectively compact, we deduce that log of OI G V divided by V UG is at least V for some constant V. For some now, the fact that the support of mu compact implies also inequality from the other side, that log of OI G V divided by V is bounded by some constant M or some M. Okay. Yeah, when a student prepare a seminar talk, I usually expect him not to lecture with a paper in his hand, because if he does it, it means that he didn't prepare well. So, but anyhow, he wrote so compactly the computation, so it's much better to follow exactly what he wrote. So Taylor expansion, Taylor theorem, says that e to the x minus 1 plus x is smaller than x squared for x which is smaller. Okay, this is an exercise. If you take the expansion of e to the x, then you have 1 plus x squared over 2 plus, and if you sum them for small x, you see that it's less than x. The exercise. So if you combine all the data that we have, you get that the integral over g of v, now let's take some delta, and later we will say what we require from delta, or I g v to the delta, the mu is equal to the integral of the exponent of delta log v divided by rho I g v, mu, which is smaller than 1 plus this. Now I'm using this Taylor estimate, 1 minus b delta plus the integral of the g of delta square log square v divided by rho I g v, which is smaller than 1 plus b delta plus delta square m, when delta is less than 1 over m. Delta less than 1 over m, Now set C of delta to be 1 minus B delta plus delta square M, and again see that for small delta, let's say delta less than B over M square, we have that C is small. Computational. I'm sorry, but it's a bit tedious, but it's yeah. Anyhow,
Is the minus missing because
where is the minus?
well, maybe there's a minus missing in the
Yeah, there is a minus missing. Yeah, there is here should be. This what you mean?
no, I meant because the what's inside the log is the other way around. The C support news compact log then Y G.
What? From here,
No, take 2 lines up.
2 lines up.
You see,
Here?
yeah, and then the fraction is reversed in the bottom lines.
Okay, but
That's why I'm asking. Maybe there's a minus missing.
Check the
There is a minus
inequality.
here.
Yeah. To check the original inequality, which we want to prove is exactly that.
okay, I let you meditate on that later. It will exactly what is written and it's fine. Yeah, I hope to somehow finish with the computational stuff before the break and get the fruits after the break. So the nice stuff will be after. So I will have a couple of more. I will have two more technical lemma like this, and then we will have this Margulis function.
WI coming?
Sorry?
Where did WI come in?
I speak about rho I. So at the end, I do it, there's finitely many I, and I consider all of them together. For each of them, I get some constant which is smaller than 1, but since there are finitely many, so.
No, even fix, I don't care, but why,
What?
what WI? I mean, you integrate over G, so it's.
V is in WI.
V is in W.
I assume V is in WI.
Yes. That was in the lemma. The lemma was. Yeah. Okay. So some notation. Okay. So we will construct this on the space of lattices. So for a lattice, let delta inside Rn be a lattice. A subset, a subspace Rn L is delta rational if delta intersect L is a lattice L. Then we denote by D of L D of L, which is I write D, but I mean D delta that way. Delta D delta of L is the volume of L divided by L intersection with delta. And just remark that let's note that D of L equals to the norm of U1 wedge U I in the norm inside WI from before, where this is the basis. U1 up to UI is a basis for a delta intersection. That's
A Z basis.
yeah, a basis like a generating set of visibility, and yeah, Z basis. So this norm is the area of the parallelogram, if you want, spanned by this vector over on the solve this vector and then zero, and in particular, d of Rn is 1 if and only if delta is fully modular, so it's volume 1, and d of 0, we also we assume that d of 0 is 0, so d of the 0 vector space is 0. A is 1, so so that's this. We want to make the assumption. Would be convenient. Actually, no, I don't discuss here. Oh. Okay. Now a simple lemma, which you tell me if you want to prove or leave it as an exercise. So let L and M be delta rational spaces, then D of L times D of M is at least D of L intersection with M times D L plus. Do I write a proof or not? Okay, it would be 5 minutes, so let's start. Yeah, I'm going to use this line. Yeah, okay. So let U1 to U I be a basis for intersection. Yeah. Delta intersection M, and complete it to basis. Basis, I don't know where U I U1 up to UI, let's say V1 VK to L and U1 up to UI and W1 WL to M section delta. Then you see that D of L intersection M is just U, the norm of U, the I of U, and D of L is the norm of U wedge V. Okay, I should say what is V. It's clear what is U is the wedge of that, V is the wedge of that, so, and W is the wedge, and D of M is D of M is the norm of U wedge W, and D of L plus M is bounded by the wedge of U V W, right? Because if you want, if you take all of them, U, V, and W, you get something that span the intersection of delta plus L plus the intersection of delta with L plus M, but maybe it's not a basis. Maybe that's something small. So that's why you get this inequality. Now, in general,
Isn't it zero when
It's mostly zero, yes.
what is zero?
if let's say V
If they have an overlap,
if they have an overlap, then it will be zero.
Yeah.
correct.
No, but the overlap is exactly the UI. There's no overlap.
Ah,
Yeah.
there's-
The overlap is exactly UI. Yes. Yeah. Okay, now in general, a factor about wedge product is that you always have such an inequality. U V, okay, but U V wedge W divided by U is bounded by U wedge W divided by U times U wedge V divided by U. So the result for if you combine. And this is for any tree vector, you have this inequality because if you think about it a moment, it's obvious. Inequality, you may assume that the norm of U is 1, if you want, and then this is the area of one parallelogram, this is the area of another parallelogram, and this is the area of it's like a 3-dimensional parallelogram, but and you use the fact that yeah, it's shorter. Yeah, I mean, okay, some vector. The height in a triangle is always smaller than the edge. So yeah, so it's really elementary fact. Okay. Anyhow, watching Margulis doing linear algebra is always impressive, and then we deduce the following lemma. Yes. So okay. Oh, now we introduce the alpha function. Yes. So the alpha functions. That's patient. I don't want to rush, so maybe today will be a bit technical, but next time we'll have the fruits. I don't know, maybe at the end of the day, at least we will see that SL and Z is the lattice in SL and R. And next time we deduce that every arithmetic group is a lattice. Always. But this will be nice. No more computation. But so today will be a bit computation. I mean, so so for I between 0 and n, define alpha I of delta to be the maximum of 1 over d of L, where L is delta rational and I dimension. It's the maximum of that. And note that delta, so alpha 0 of delta to be 1, and alpha n of delta is 1 if and only if delta is unimodular. So, which means, so we call that we denote by omega n to be the set, the space of unimodular lattices. Identify it with SLN R mod SLN B. So basically, we want to show that this space has finite volume. The Haar measure of that is finite. So that's a target for today. Show that the Haar measure is finite, and we'll do it by constructing a Margulis function using this alpha icon. So we'll show that some clever way of summing the alpha I, producing the Margulis function. Note that this alpha I, all of them are proper functions. For I, okay, if alpha 0 is not proper and alpha n is not proper, but if you take any other I which is strictly bigger than 1 and strictly smaller than n, then alpha I is a proper function, because the only way to go to infinity in the space of lattices is by Mallet-Criterion, is by Mallet-Compact Criterion tell you that you go to infinity if and only if the lattice is shorter and shorter vector. So, and then if you translate it to that, it will mean that the alpha I must not proper. Okay. Yeah, we're close to the end of the technical stuff, but okay, let mu in probability of SLNR, probability measure SLNR with compact support.
Alpha 1 is also not proper. Alpha 1, alpha n minus 1 are not proper.
No, alpha 1 is proper. Alpha 1, if you want, is 1 over the length of the shortest vector. The only way to go to infinity in the space of lattices is that alpha 1 will go to infinity. In some sense, it's not clear to me. Okay, it's clear when you read the lemma and the proof, but why is it not sufficient to work only with alpha 1? Somehow, okay, I see why in its proof, but again, I think it would be nice to combine this Margulis function, and it's very fruitful to construct Margulis functions. And I encourage you or us or to try to mix this approach and the approach from the other work with Ariel Margulis and see what, okay. So let mu be such with compact support, and then we have two constants, W mu will be just the maximum of the norm of rho I of G plus minus 1 if you want, such that G belong to the support and I in 1 and minus 1. And so this some number. And the other number is C of M delta, is the number that we showed before that for small delta is smaller than 1, will be the maximum of the integral of G as we did before. V to the delta divided by G V to the delta U. And again, we take V inside Wi, I between 1. So now, basically want to construct the Margulis function. Form. So the integral G of alpha I of G delta over delta dμg bounded by C times alpha I delta plus W to delta times maximum J smaller than maximum. Overall, think that this makes sense. Square root of alpha I plus J is to delta maximum alpha I plus J times alpha I minus J. Overall J that this thing makes sense. So we want J to be positive, smaller than n minus I or something. J is positive and smaller than the minimum between I and n. Okay. So that's one lemma. Let me write the next lemma. And the proof of this one is technical. And yeah, let me write it. Then we discuss if you want me to write the proof of propositions. That's the main result of one computation we did. So let U in the probability SLN R satisfying one, 2, and 3. You remember in one of the lemmas we had 3 conditions. One of them that it was compactly supported. It was symmetric, and it was inside the supported on the positive definite matrices and generate an irreducible subgroup. That was 1, 2, and 3. I think 2 was both that it's compactly supported and of positive definite matrices. So, so let me with such a measure, then there is C smaller than 1 and delta bigger than 0, such that for every I, we have that A mu, the averaging operator, which is exactly what is written here. So basically, A is repeating this lemma of alpha the delta is bounded by C alpha I. The delta of W delta times maximum J as we go, square root of alpha I plus J times alpha I minus. Okay, I just added this lemma. This is also delta. Okay, now B, so A is just repeating the lemma, and B it says that there is a proper.
So you also have the power of the
It's the same. It's just this is just repeating that. Okay. And this is exactly what is written here. There is a proper Margulis function. There is a proper positive constant. Proper positive continuous function. F on omega n r such that n two constants C1 which is smaller than 1 and B such that A U F is smaller than C1F. That's exactly what we want. And this proper function is basically the sum and yeah. Okay. You see, by the result of last, let me just take the consequence and then we. Oh, Larry. I owe you a proof of both level proposition, but oh, Larry. S and NZ is a lattice in SLNR. See, this now is immediate because there is a proper. This statement is equivalent to say that the Haar measure of omega n is finite, which is exactly what we deduced last time when we had a proper Margulis function. So all this work is to construct a proper Margulis function, and then we deduce that And later, we can forget what was the Margulis function, and just from the fact that there is, we will reduce, that any arithmetic group in any semi-simple group is the lattice. So all the conclusion will be nice and not computational, and all this work was to construct, or is, because I owe you a proof still, is to construct a Margulis function. And you see, somehow I think that it should be enough to use alpha 1, but this lemma tell you that if you average alpha 1, you bound it in terms of also other alphas. So you average each alpha I and you bound what you get in terms of the other alpha. So that's why I use all of them. The Margulis function that it takes, I will tell you the secret already. The Margulis function that it takes is the following: f will be the sum of epsilon to some power times alpha I is delta, well, okay, when epsilon is well chosen and delta is well chosen and q of I is I times n. So the sum, this will be the Margulis function.
No, there's nothing, it's not a lot, okay. It's not the same rule.
Sorry?
No, yeah, we had a lot of work with
This was Q. This is Q. Ah,
it is not here.
okay. That's good. Or?
That's okay.
One of them.
No, this is G. So what was the point? Now,
It's
like this. Anyhow, yeah.
Next is,
Yeah, and that's how to construct a Margulis. So we need to do this computation, and then we get the Margulis function, and we reduce that. It's I think it's quite impressive proof, and I think it's worthwhile to try to simplify it. One way to simplify it is that to use only alpha 1. I think it should be good. And the other approach would be to connect this and the radius approach. Yeah, so we need to do this computation. Let's do it after the break. Yeah. So what the book is technical lemma. Let M be a delta rational subspace. The delta rational subspace. Then for GG, we have that GM is both G delta rational. And if
G is less than enough.
G is ln, yes. If V 1 up to Vn or Vi is the basis every single for delta is the basis, then you see that the D of M, which is the co-volume, is just the norm of V1 with VR. And the D of with respect to G delta of GM is the norm for IG V Y of G of the vector V1. So from this and what we already did, we see that the integral over G of 1 over d G delta GM with our delta is at most C times 1 over d delta of M with our delta. Okay, this is the level we had before because these are just nodes. Now, and yes.
The transformation OIG is acting only on V1 or
No,
or
why is the representation on the wedge form? If you want, what is written here is GV1 wedge GV2 wedge GVI. And okay, for G in the support, by the definition of omega, for G in the support, we have that d G delta of GM divided by d delta of M is between omega and omega E. Like if you erase the definition of omega, but omega basically was the maximum of the norm over the, of rho I of G over the support. Okay. This is how we need. Now there is some delta rational space, I space, let's call Li, such that alpha I of delta is exactly 1 over. So fix this Li and define a set. Let define the following set psi I be the set of all delta rational subspace delta rational I space such that I space is L such that d delta of L is less than omega squared d delta of L. Okay, this could be a singleton or some finite set. Or maybe, yeah. Okay. And observe from this, from what is written here, that for any space which is not there, L not psi I, for an I space for L of dimension I, we have that d g delta of GL is strictly bigger than d g delta of GL. The only one that can give you smaller values for some G, and for every G. If you have that for some G, this one gives you smaller value, it means that, yeah. G of Li is smaller than, if you do it just for Li, it's smaller, but when you multiply by G, maybe one of them increased by W and the other decreased by W. So if you're in psi I, maybe you get smaller value, but if you're on outside psi I, you cannot get smaller. So, okay. So, therefore, if it's only a singleton, psi I is just Li, then we have, and we have clearly that the integral over G of alpha I of G delta, the delta is less than C alpha I. Now, suppose now that it's not the same. Psi I is strictly bigger than Li, and let M inside psi I, which is not Li, and leave M plus L, we denote it by I plus J, where J is some positive number. And now, from the lemma that we had before, we get the following. So, for G in the support, we get that alpha I of G delta is at most omega alpha I delta, which is equal to omega divided by d delta of Li, which is at most omega square divided by, okay, you check it later. Every line is easy to check. The M. Now, this from the one of the lemma that we had, most square root of d delta of the intersection. Intersection times d delta the sum, which is at most omega square times square root alpha I plus 1 delta times minus. It's good not the smart with J minus J. Okay. Therefore, line. It's if psi I is not I, it's really bigger, then we have the integral over G alpha I G delta. The delta is smaller than omega 2 delta maximum over J is 0 and the minimum I J minus I and I and N minus I and of the square root alpha I plus J and alpha I minus J okay. So, which is okay, that was the most technical computation in this paper and also in this course. Okay, so let me spend another few minutes to do the other technical part, which is the proposition, and then we're done. We will have the Margulis function and we can just use it. But you see, you bound the convolution. This is the convolution, right? This should write it in mu. So this what is written here is that is a mu of alpha I to the delta. And so alpha I delta evaluated at this point. And somehow it would be nice to estimate of alpha 1 and to bound it on the other side by something which don't use the other alpha, just alpha 1. And I think it's doable because you can probably bound the other.
Slides?
Sorry?
Shortest slides?
Yes. Yeah, I think. Yes, I think it should be. So here, yeah. Okay. So let me now write again the proposition, and this will be the end of the computational stuff. This side. So I do that. So with the proposition. So mu satisfying the condition 1, 2, 3 probability measure on SLN. W is what was before, and C is what was before. Then A, there exists C smaller than 1, so it is smaller than 1 by the level that we had, and delta. Okay, that's what you just showed. But so there exists a proper Margulis function and proper function, proper positive function f on omega n, which is SLN R mod SLNV, or if you want the space of fully modular lattices. And two constants C, which is smaller than 1, and B, that the convolution is smaller, it's point-wise than C1F. So that's what we need for the finiteness of the volume, and this is the okay. So I need to tell you what is the function.
You also said something about the C0, or is this the same?
Sorry? Yeah, before there was C0 in the previous, and now C1 will rely on C0, but it won't be C0. Okay, so proof. So set Q that's Q of I equals I times n minus. Then the recomputation shows that 2 Q of I equals minus Q I plus J minus Q of I minus J equals 2J. Let's leave it for you. Therefore, every I between 1 and n minus 1 and epsilon which is smaller than 1, we have the following. A mu of epsilon to the Q I alpha I delta smaller than C times epsilon Q I alpha I delta plus W to delta, that's the same, right? The maximum to J of epsilon Qi minus
C is a C.2.
Qi plus J plus Qi minus J square root of epsilon Qi plus J alpha I plus J epsilon Q I minus J alpha I minus J. Yeah. Okay. Maybe. What's the question?
What's C?
Yeah, from the previous level. This is what we get from the previous level.
You mean a minus Qi minus J?
I minus.
I don't understand.
Yeah, maybe.
Oh.
Okay. Yeah, and that's it. Okay. And then if it's smaller than C epsilon to the Q I alpha I delta plus epsilon omega delta maximum sensing and epsilon Q I J alpha I J delta epsilon I J alpha I J.
Epsilon is the Q,
Yeah. Epsilon to the Q.
and here it's alpha I minus J.
Here it's alpha.
No, above, one above. Okay, I'm finished with
Epsilon. Ah, yeah. Yes. Yes. Okay. Okay. Now set. Now we decide what is epsilon. Epsilon will be 1 minus C times 3 N W to delta minus 1. And then F will be the function sum I go from 0 to N of epsilon to the QI alpha I to delta. Quite impressive, no? We do all this to prove Harish-Chandra. And now, okay, you recall that alpha 0 is 1 and alpha n is 1 because we are on the unimodular lattices. What this implies, then we get that a nu f is smaller than 1 plus 1 plus CF plus n epsilon omega to delta F, which is 1 plus 2C over 3 F plus 2. So set C1 to be 1/3 of 1 plus 2C. Recall that C was smaller than 1, so we will find. And recall finally that alpha I, where I is bigger than 0, smaller than n, of both. That's finished. Yes.
This epsilon,
Yes.
one of the epsilons in the third line, shouldn't be the epsilon in power of j?
Epsilon here?
No, the one before, next to the omega, in the third line.
This is the third line.
Yeah, this one,
Epsilon.
because this equation. No,
Look. Margulis did. No, just epsilon. Because I use the equality, I use this equality somewhere.
yes, so
And,
you got it.
Yeah, I checked it before, and I was convinced that there was no mistake here. So, and now I copied it as well. So yeah, that's fantastic. So yeah, so from now, actually, I don't know if we can do Borel Harish-Chandra for 20 minutes. Yeah, let's start. No?
But for any of this like lemma proposition, we didn't use anywhere basically that we are specifically in SNN or we're using specifically SNNZ, right?
No, I mean, all this was done specifically for the alpha I function, which are function on lattices in Rn. So
Yes, exactly.
So we consider, yeah.
I mean, this works for any cube, like any group modulo the Z ones.
Yeah, I mean, okay. The point here, like, we reduce the distance finite point, and now, but this approach, from this approach to reduce the same for any rationally defined subgroup is easy. Let me just okay. Let me say a few words. So we have 20 minutes. So let me start.
Can you say anything about this Margulis function?
What is it?
No, how do you come up with it?
I didn't come up.
No, I know.
Yeah, it's quite impressive. We think.
In every paper that I read of Margulis, he has all these computations that somehow come from nowhere.
Yeah, he's really fantastic in linear algebra. That's yeah, it's all linear algebra, right? But it's yeah. I mean, no, I think it will be worth to yeah, Margulis functions are really valuable. So once you manage to prove that something is Margulis function, you get some conclusion.
You call it Margulis function because only Margulis finds Margulis function.
Margulis attributed to Liam this property. But let me just okay. Let's now see a lemma. So let G be okay. Yeah, that was the let's give it like finiteness of volume and no volumes. And on 20. So there is still something to say, but let G inside SLN be close, connected, semi-simple, irreducible. Semi-simple without compact factor, irreducible. So it means that it acts on R irreducibly, so we want to start space without compact factor. And let X inside omega n. You remember this is the page of unimodular lattices. Suppose that the orbit that G times X is closed in omega n. Then UG, let's call it sigma nu. Then yeah, okay, mu. It's not the same. Before mu was a probability measure. Now it's a measuring used from R measure. So mu G of Gx it's finite. Well, u is the Howe measure induced from R on so you see, this is basically tell you that
Maybe from you is you mean there is, what do you mean? From you is induced from the harmony. The stabilizer is for finite.
the stabilizer is discrete. Yeah, that's what it means. It means that it's a lattice. The stabilizer of X is the lattice. What is the stabilizer of X? So if X was Zn, then the stabilizer of in SNN was just SNNZ, and the stabilizer in G was just G. And the proof relies on two results. So one is a very useful result by Mostow. Here is the theorem of Mostow. I can use many times. It's enough to be reductive, but a semi-simple group G inside SLN are semi-simple, then there is a conjugate G in SLNR such that G inverse is adjoint invariant. We want transport invariant. The adjoint. Yeah. So that's the theorem of Mostow, which you should keep in mind. It's every semi-simple group inside SLN you can conjugate to be transport invariant. It's very useful. Another fact that I want to use is I can write it as exercise, but it's not a good exercise because if you don't have the background from the theory, it's too hard, and if you do have, it's maybe too easy. But I think in Borel's book you can find exercise which imply it easily. If G inside SLN is, let's say, transpose invariant, adjoint invariant, and has non-compact factor, then you can find a compact set. Then there is K, let's say there is a compact set U inside G compact consisting of positive definite F-adjoint matrices such that omega generates G. So it's very easy to generate a leaf. Basically, but the question is whether we.
Joint invariant is inside the sum.
It's inside SLN. It's transpose invariant, let's say. Yeah. Transpose invariant. Maybe I should call it.
Oh,
The adjoint is just transpose. So I will not discuss this exercise now. I just assume it as a fact. We can maybe at some point we can discuss generating the leaf groups. But yeah, this is a. Now, but you see, so using this Moser theorem, you can assume that this G originally was transpose invariant.
Why do you say no compact factors in the fact?
What?
Why do you write without compact factors in the fact?
Because it's not true. What do you mean?
It's not.
No, if G is compact, SON SON cannot be generated by. No, here exactly. Here you need that it's non-compact. It's not true if you're compact. And this is why here we assume non-compact. It's a good question. Because later we want to prove that every arithmetic group is elastic. And we have to allow compact factors because otherwise we restrict ourselves to you want to know from lattices. We have to allow compact factor, but then we cannot apply this proposition. We will apply something else. So here, if you have no compact factor, then you have such a, and then you see you can deduce now. Okay, now you see the fact that this is closed. What does it mean? It means that if we take if you take the Margulis function from above, Margulis function on omega n, and you restrict it to the orbit, we all assume that G is transpose invariant using Moser, and then you look at the orbit of X, and if the orbit is closed, it means that the map from G modulo the stabilizer to the space is a proper map, and therefore the Margulis function that we had before induce a Margulis function on this orbit. And from this, we deduce that the measure of the orbit is fine, the G measure. Okay, I will explain it in more details next time. But this is not the end of the story. The corollary would be.
Tsachik, are you sure that how you stated Moser theorem is correct? Don't you have to take the adjoint? Is it true for like G itself or for the adjoint G?
It's true. I mean, what do you mean? Semi-simple. I say maybe you need to adjoint.
I'm pretty sure you need to take that.
I don't see. But, okay, let's.
I mean, anyway, it doesn't really matter.
It's okay. Anyhow, Moser is for reductive group in general. Okay, let me say one more thing, right? Another lemma is the following. So let G inside SLN R be a Q subgroup. So it's a bigroup defined over Q. Then the map from G mod G Z to omega n, which is SLN R on SLN Z, is proper. Now, if you combine both this lemma with the previous proposition, you get that GZ is a lattice in G. In that, if G have no compact factor, okay, why is this true? Yeah, since I will not give you full proof of Borel Harish-Chandra today. I will come back to it next week. So I'll repeat also it's two propositions, this proposition and lemma. But let's at least explain the proof of the lemma because it is straightforward. Again, I need to apply. You know, Malchev theorem. If you have a algebraic group and you have a subgroup, then there is some representation such that the subgroup is the stabilizer of a one-dimensional subspace, right? You
Actually, for Chevrolet.
sorry? Chevrolet. So yeah. So we call Chevrolet. How do you write Chevrolet Q1?
E1. Okay, for double.
Sorry?
There's an A for double. Yes.
No, instead of the
Instead of the Chevrolet theorem say that there is a Q representation or from SLN to, let's say, SLM, and a Q vector W inside QM such that G is the set of all G in SLN such that G W belongs to the line spanned by W. So GW equals W. Well, W is the span, the outspan of W. So that's Chevrolet theorem, and we're going to apply it to prove the lemma. Now, I see that I need something in the lemma. Not G is not every group, but let G be a subgroup, a Q group, without Q power. Then the map to proof. Okay, the hint is that you use Chevrolet, but we'll do it. I don't want to fight against time, and we need time for lunch and then the midrasha. So let's leave it for next time. But once you have Chevrolet, this becomes straightforward, and you see that now if you have a G, which is both semi-simple without compact factors, and in particular it doesn't have rational character, therefore GZ will be, this map will be proper, and therefore the image of the orbit will be closed, and we get that it's a lattice. But that will not that will not cover all the cases because it would be enough for non-uniform lattices, but okay, so any question about sorry about today was a bit technical.